to continue with our review of Chapter 3 today. We're going to look at limits at infinity. If you have any questions, be sure to let me know. And this is for those of us who can't be in the class physically, but also a good review for all of us. Alright, so let's look at limits at infinity. So imagine I have a function that looks like this. And we have these horizontal lines that I trend towards in this direction. If I go out this way, I'm trending towards this line here. And as I go out this direction, my graph trends towards that graph there. What do I mean by trend towards? It means if I zoom in, this graph is going to get closer and closer to that horizontal line. And the further I zoom in, the closer I get. The further I zoom in, the closer I get to this line. So if this was the line y equals a, and this was the line y equals b, then I would say that I have horizontal asymptotes if y equals a and y equals b. And the technical definition of a horizontal asymptote in algebra, we say it's a horizontal line the graph never crosses. Well, here we see a picture where I have two different horizontal asymptotes and I cross both of them. Okay, so what is actually the definition of this? The horizontal asymptote is your limit point as x gets incredibly large. I mean, I drew the arrow here going out this way. What I'm saying here is x goes to infinity. And what I'm saying over here is x goes to negative infinity. So we can say if the limit as x approaches infinity of f of x equals L, then f has a horizontal asymptote at y equals L. And that is the technical definition of a horizontal asymptote. We could do the similar thing with x approaching negative infinity, okay? So you can, and they don't always have to be the same thing. You can approach, as the picture we have here, you can, as you approach infinity, you hit one limit point. As you go to negative infinity, you hit another. And I'll show you how this works, how we do this. We can see the picture. Hopefully the picture makes sense. But how do we do this algebraically? Alright, so we'll just go over some examples to help answer these questions. To really make sense of this, though, we need a big theorem that says if we have something greater than 0, then the limit as x approaches infinity of 1 over x to the r equals, well, let's think about it. Okay, so if you had x and 1 over x to the r power, whatever r is, if I plug in 1, I get 1. Let's just say, how about let's let r be 1 just for our illustration, just to make sense of it. If I plug in 10, I get 1 over 10. Okay, so what the example I like to tell students about with this is saying the 1 over x is the percentage of the pizza that you get when you're sharing it with x people, right? So if you share a pizza with 10 people, you get 1/10 of the pizza. And the more people walk in the room, what happens? The smaller your share of the pizza gets. So if a million people walk in, then you don't get much of a pizza, right? And so what's happening is as x is going to infinity, what is 1 over x doing? So the more people who walk in the room to share this pizza with you, the smallest your percentage gets. If an infinite number of people are in the room, you're going to get 0% of the pizza. And I hope that makes sense. We can make sense of this with some geometry. If I graph 1 over x, I get this type shape. And so as I'm going to infinity here, what's going on? I'm trending towards 0. So the answer to this theorem, the limit as x approaches infinity of 1 over x to the r, where as long as r is positive, we get 0. And that is a very, very important statement. It's something we need to keep in mind. And that's going to be the tool we use to evaluate limits at infinity. So for example, let's take this rational function, 4x cubed plus 6x squared minus 2 over 2x cubed minus 4x plus 5, and let's figure out what's going on as we go to negative infinity of this thing. Okay, that's the idea here. And the trick to doing this, and I don't usually like to say, let's put in some mathematical tricks, but the idea, what you want to do is to divide the numerator and the denominator by x to the r, where r is the highest exponent in the denominator. Okay, so for example here, I'm going to divide everything by x cubed. Alright, now what you're technically doing here is I'm not going to divide by x cubed. I'm going to multiply in 1 over x cubed. And why did I pick x cubed again? Because that was the highest power of x in the denominator. Okay, now as I distribute this across, so we just do some algebra, you get something like this. And that looks actually a lot more complicated than what we started with. But if you pay attention to what's happening to each term in this expression, this is actually going to make things a lot easier on us, because notice here the x cubes cancel out on the 4 and the 2. On the 6x squared over x cubed, a lot of it cancels out, and nothing cancels out on the 2 over x cubed. Down here in the denominator, I have the 4x over x cubed simplifies the 4 over x squared, and then the 5 over x cubed just doesn't do anything. Okay, now, how is this helpful? Because of the theorem we just said. The limit as x approaches infinity, and this will be true for positive or negative infinity, 1 over x to the r goes to 0. Alright, so first let me write a simplified version of this just so we can see it. So there it is, and then now notice as x goes to infinity, what happens? That expression is going to go to 0. 2 over x cubed. Well, that's 2 times 1 over x to the r power, r being positive, that's going to go to 0. 4 over x squared, yeah, that's going to go to 0 as x, because you got to imagine x is getting incredibly large in the negative sense. It's the absolute value is incredibly large of these values. It doesn't really matter what the numerator is. The denominator is going to push this thing to 0, right? I mean, this would be like dividing the 5 over x cubed, for example, would be like dividing 5 pizzas among so many people. As that goes to infinity, you still get 0. So when all the dust settles, what do we end up with? Simply 4 halves or 2. There's my limit. Okay. Now in college algebra, what we said was if the degree of the numerator equals the degree of the denominator in a rational expression like this, you have a horizontal asymptote that is just simply the coefficients of the numerator and the denominator, which is exactly what we got here. We got this 4 over 2. Okay. Now, I could have told you that this is the answer ahead of time, because remember, we're talking about the trend. So again, the limits at infinity, what we're doing is measuring the trend of f of x as x gets incredibly large. So when I have something like this, and I add some stuff to it, actually what happens, the other parts don't really play a role in this because they all trend to 0. Just, you got to think of it like this. If I handed you a check for $1 billion, 35 cents, you don't even hear the 35 cents after I say a billion, because the largest terms are what's dominating the trend. And since the largest terms are equivalent, what I mean is the x cubed, this is going to trend to the 4 halves. If I had something like this, 4x cubed over 2x squared, plus some other stuff, some smaller stuff, well, what's dominating now? You have a square term in the denominator, you have a cube term in the numerator. A billion cubed is so much larger than a billion squared. The numerator is outpacing the denominator. You're going to end up going to infinity. The numerator is outpacing the denominator. If I had something like this, where I have 4x over 2x cubed, now what's going on? The numerator is growing to infinity, but not as fast as the denominator is, right? Because again, a billion cubed is so much larger than a billion. So in this case, the denominator is growing faster, and we trend to 0. Now this is kind of how we handled it in college algebra. We just looked at the degrees of our numerator and denominator and made some rules based on the way they compare, and then just drew our results. I think that's a good way to handle these conceptually. The problem is that not every question can be handled so simply. So let me give you an example. But would the math that we just did with the previous example work in this, by this pattern? Absolutely. It would definitely work that way. Well, let me show you another example though. Now in this example, we're going to try to find the horizontal asymptotes of this function. F of x equals the square root of 3x squared minus 2 over 5x minus 11. Alright, now if I'm trying to do the trend thing that I was talking about earlier, well, I have x to the first power in the denominator and an x squared under a square root in the numerator. Are those kind of the same thing? Does this thing limit to 3/5? That might be a good guess. I don't know. Let's try to figure this out. And a couple things we need to remember. First of all, we need to remember the absolute value of x. Why the absolute value of x? I'll explain in a little bit, is negative x for x less than 0, and it's positive x for x positive. Okay, so in other words, if I plugged in negative 6, which would be negative, then my answer is negative 6. That's what absolute value of x would mean. And the reason I bring that up is because the square root of x squared is actually the same thing as the absolute value of x. So when I see that I see the square root of 3x squared, I have to think that is the square root of x squared is an absolute value of x. That's why absolute value of x plays into this. So here we're going to take the limit as x goes infinity. Because it says asymptotes, we're going to have to go both directions, positive and negative infinity, and maybe we'll get different answers. So the limit as x approaches infinity of this thing, I'm going to divide everything by x to the highest power of the denominator. So that would be like a 1 over x. But the thing is, I'm going to have to interact a 1 over x with a square root. And so the way I do that is actually I have to remember that the absolute value of x is the 1 over x squared. So I'm actually going to multiply in 1 over the absolute value of x into the numerator and the denominator. Right? So when I do that, approaching it this way is what allows me to bring in the absolute value into the square root, because the absolute value of x is the same thing as the square root of x squared. So I end up with this expression, 3x squared over x squared minus 2 over x squared, all under the square root. Okay, now as x goes to infinity, since those are going to be positive values, I see here that for positive x, it's just absolute value of x is just x. So that means that x and absolute value of x are the same there. They cancel out. Of course, that cancels out. And so I end up with the limit as x approaches infinity of the square root of 3 minus 2 over x squared, all over 5 minus 11 over x. Okay, and now I can see that the 2 over x squared is going to trend to 0 as x gets incredibly large. The 11 over x trends to 0 as x gets incredibly large. And so this thing does end up being root 3 over 5. Okay, so there is my horizontal asymptote as x goes to infinity. Alright, now we also need to consider, though, what happens going to negative infinity. So let's do the same thing. And actually, most of the work is going to be exactly the same. Okay, so I'm still allowed to bring in the absolute value of x inside the square root, because the square root of x squared is the absolute value of x, so that's not a problem. Here's the only issue. This is where it changes a little bit. I can cancel out that. That's not a problem. The 2 over x squared is still going to go to 0. The 11 over x is going to go to 0. But when I cancel out these, that's going to be a problem, because I'm trending towards what? Negative infinity. And that means I'm plugging in negative values into the absolute value of x. And when I plug in negative values into the absolute value of x, I actually have negative x. So when I cancel out x over the absolute value of x, I mean, think about it. If I canceled out negative 6 over the absolute value of negative 6, I don't end up with 1, do I? I end up with negative 1. And that's exactly what's happening here. These cancel out to give me a negative 1. Okay, so that does change some things. Let's see. That means now I have the limit as x approaches negative infinity of the absolute value of 3 over 2x squared. That stays the same. Negative 5, not positive 5, minus 11 over the absolute value of x. And just as before, these are going to go to 0. And so this time, I end up with 3 over 5, but it's negative. So I have different horizontal asymptotes. They are y equals square root of 3 over 5 and y equals negative square root of 3 over 5. Okay, let me show you one more thing that you encounter with these. So if you had something like this, the limit as x approaches infinity of x squared minus 3x. Well, notice that that would be kind of like infinity plus infinity, which is not something you should write. But we can understand then that this thing is going to trend to infinity as x gets incredibly large, right? But sometimes we might have a situation where it's not that clear because it has an infinity minus an infinity situation. So one like this, for example, notice as x gets incredibly large, I end up with an infinity minus infinity situation, and I don't know what that is exactly. So we're going to have to do some sort of algebraic manipulation on this thing before we can evaluate it. And when I have a square root like this, that tips me off that what I want to do is multiply the conjugate into this. And whatever I do to the numerator, I have to do to the denominator as well. So at first this thing looks like it's going to get way more complicated, because now I have the limit as x approaches infinity, I have a big denominator down here, and hopefully the numerator cleans up a little bit. And it does. That's the whole reason we did this. Because notice as I FOIL, so if I multiply the first two terms together, the square roots cancel. I just end up with 9x squared plus x. When I multiply the outside terms, I get this ugly expression, but the inside terms also give me that ugly expression, just negative, and so the two of those actually subtract out. So the middle part that has these radicals involved don't become a factor. And then lastly, I have minus 9x squared. So when I simplify this, I end up with, well, actually just x in the numerator, right? In the denominator, I have this expression. Okay, so now as I'm going to infinity, I got to divide by the highest power of the denominator, which would be x or the square root of x squared. So I'm going to divide by 1 over absolute value of x, just like we did last time. But it's not going to really play a role here since I'm going to positive infinity. So I end up with x over x, right? Because x is positive, so the absolute value of x can just be the x over x. Bringing the absolute value of x under the radical, I end up with square root of 9x squared over x squared plus x over x squared, and that is all under the radical, plus 3x over x. So now as things cancel, I end up with, before we take the limit, let's see, a 1 in the numerator, square root of 9 plus 1 over x plus 3. Now letting x go to infinity, the only thing that goes to 0 is that. And I end up with 1 over the square root of 9 plus 3, which ends up being 1/6. And so there is your limit point for this expression, which is not obvious right off the gate, right? Our rules that we learned in algebra would not help us here. Now, because that last example was not obvious, I feel like we need to look to Mathematica to get a picture of what we're talking about here. So if I graph the function 9x squared minus x in square root minus 3x, and let's let x go from 0 to 10. Hopefully that helps us see that horizontal asymptote. I can definitely see the trend line here, but wait a minute, this is at negative 1.67. Shouldn't we get the value of 1/6, which should be our horizontal asymptote? Well, that's way up there, so what did we do wrong? Aha. We said 9 squared minus x, it should be 9 squared plus x, and there we can see it. And actually, if I did a manipulate around this, and instead of going to 10, I went to a value a, and we'll let a go from 10 to, how about 100? I think we can see it even more clear as I drag a across. You can see here that my y-axis is getting very, very small. Look, I'm at 1.662 up to 1.666. And as I keep going, I just get closer and closer to that horizontal line. Also in Mathematica, you can do this. You can just say limit. We could take the function that we just looked at, and I want x to go to infinity, and it'll just pop it out for you. Alright guys, this is limits at infinity. I hope this makes sense. Remember, horizontal asymptote's not a line that the graph can't touch. It means the trend line as we go out towards infinity or negative infinity. I've shown you the tricky parts of algebra that may be involved in this. Again, if you have any questions, let me know.